this video, we will be looking at a new number, e, and we're going to discover its derivative. Now, before we get into that, we have to see what is this number e, what does it represent, where does it come from? So we're going to do a little refresher on compound interest. Compound interest is A equals P, the principal investment, times 1 plus I, where I is the interest per compounding period, all to the power of n. Now, the way this number e was discovered was by thinking about what happens as the number of compounding periods gets larger and larger. So we're going to imagine a $1 investment, so our principal, P, is going to be $1, at a 100% interest rate. So that means I is going to be 1, so 100% divided by 100, which is 1, divided by however many compounding periods we're testing, and then to the power of n, where n is the number of compounding periods in that 1 year. So if we're compounding once a year, it'll be 1. Twice a year, it'll be 2, and so on. So what we have here, you're going to calculate each of these values. So if we have 1 compounding period, if we have 2 compounding periods, 3, and we're going to see what happens as the number of compounding periods gets larger and larger. So for example, for the first one, 1 plus 1 is 2, to the power of 1 is 2. 1 plus a half is 1.5, to the power of 2 is 2.25. And you're going to keep doing this. So please feel free to pause the video and punch these values into your calculator and then come back when you're ready to see the conclusions. All right, so these are the values that you should have gotten. Now, what we can see, the value gets larger and larger, but we never seem to get past 2 point something, like we never get beyond 3. And we're getting larger and larger, but as we get closer to this 2.7, the increase stops being as dramatic, and it looks like we're just approaching this 2.718 something value. And that's actually the value of E, which we call Euler's number. And this value is found by taking the limit as h approaches infinity of 1 plus 1 over h to the power of h. And that's exactly what we were doing. We were making our h values larger and larger, and we were investigating to see what this value is approaching. And it approaches this number E, which is Euler's number, and it is approximately 2.718281828, and so on. Okay. Now we could have also found this value by taking the limit as h approaches infinity of 1 plus h to the power of 1 over h. We end up approaching the same value. Now that we know what this value is, we're going to find the derivative of the function e to the power of x. Now this is just an exponential function, which we've seen before, 2 to the power of x, 3 to the power of x, a half to the power of x. But here our base is specifically the value e. And if you do look at your calculator, you should have that button on there. You do not have to type in all of these decimals. So we're going to do a mini proof here using first principles. All right, so f prime of x is going to equal the limit as h approaches 0 of, we're going to evaluate f at x plus h, so e to the power of x plus h, minus f at x, so e to the x, all over h. Now when I look at this, I could factor out from my numerator an e to the power of x. Now remember, when I'm factoring it out, I'm just dividing each term by e to the x. And when we divide terms with variables up in the exponents and their bases are the same, we can use that quotient rule where we subtract our exponents. So e to the x plus h divided by e to the x is e to the h. E to the x divided by itself is just 1, and that's all over h. Now I'm going to use our limit properties, and whenever we have a function that is made up of the product of two other functions, we can just apply the limit to those two individual functions. So I'm going to do the limit as h approaches 0 of e to the x times the limit as h approaches 0 of e to the h minus 1 all over h. Now, to evaluate the limit as h approaches 0 of e to the x, well, that just stays e to the x. There's no h in that expression, so h approaching 0 does not affect it. Now, for this fraction part, I can't use any of our typical strategies of factoring or conjugate or common denominator or any of that. So I'm just going to do a little bit of a test value here. I'm just going to pick an h value very close to 0. So I'm going to use 0.001 just to get an idea of what this fraction is approaching. So I'm going to do e to the power of 0.00. Oh, actually, I'm going to put an extra 0 in here. Subtract 1 all over that same h value. And if you punch this into your calculator, you get a number very close to 1. Okay? So that means this portion here is equal to 1 or approaching 1. So I would have my derivative as e to the power of x times 1, which is just e to the power of x. So here it is. F prime of x is e to the x. So the derivative of the original function is the same as the original function itself when the base is specifically e to the x, or when the base is e. True or false? The derivative of an exponential function is also exponential. That is true because the derivative is the exact same exponential function. Now, obviously we're not always just going to take the derivative of e to the power of x. We could have a composite function where we have a function within a function. So let's look at that. So if our function is e to the x, the derivative is e to the x. But if our function is e to the power of g of x, where g of x is some other function, this is a chain rule. I'm going to take the derivative of the outside function. The outside function is e to the power of something, and e to the power of something is the exact same thing. So first I'm just going to take the derivative of that. And now my inside function is g of x, so then I'll multiply that by the derivative of that inside function. Okay? So let's try a few derivatives here. First we have 4 times e to the power of x. Well, 4 is just a coefficient and it's not going to affect anything, so it's still 4 times e to the power of x. If I had 3x times e to the power of x, this is now a product rule. So I'm going to take the derivative of my first function, which is 3x, so the derivative is 3, and then copy paste the second function, which is e to the x, plus copy paste the first function, 3x, and then take the derivative of the second function, but the derivative of e to the x is just e to the x. So there we are, a product rule. For the next one, g of x is equal to e to the x plus 5x squared all to the power 4. We have a chain rule here. The outside function is that we have something to the power 4. So first thing, bring the 4 down. The inside will stay the same, and then it'll go to the power of 3. I'll just write the inside. And now I'll take the derivative of the inside function, e to the x plus 10x. Okay. Next we have e to the x squared. So again, we have a composite function. Our outside function is e to the power of something. Our inside is x squared. So my derivative is going to be e to the x squared. I'm not changing the x squared. And now the derivative of the inside is 2x. And we're going to have the same idea for E and F. So for this one, derivative of the outside, copy paste the inside function. This is my inside function, and its derivative is 1/2 x to the 1/2, because remember, a square root is x to the power of a half. If I just want to clean this up a little bit because I don't want a negative exponent, I'm going to keep e to the power of the square root of x in the numerator. The 2 and the square root of x will go in the denominator. And because I see that square root, I know that x has to be greater than 0. All right, and for this next one, e to the power of sine x, the derivative first, e to the power of sine x, copy pasting that inside function, and now the derivative of sine is cos x. Okay. And now we have a few more, a little fancier product rule, quotient rules, chain rules, and some of them have that sine and cos from before. So let's take a look. All right, so we have e to the power of 3x minus 5 as our first function times the square root of e to the power of cos x. So we have quite a few rules here. We have the product rule, we have chain rules, and we even have chain rule within a chain rule. So let's start off with the derivative of the first function. This is a chain rule. First, the derivative of e to the power of something is e to the power of that something, and then that will get multiplied by the derivative of that exponent, which is just 3. Now I'm going to copy paste that second function. Plus, now it's time to take the derivative of the second function, and then I'll multiply it by the first after. This one here, it is a bit of a chain rule within a chain rule. However, we can clean it up a little bit. This is e to the power of cos x, all to the power of a half. And whenever we have an exponent to the power of an exponent, I can just multiply. So, okay, sorry, I'm running out of space here. This is just e to the power of 1/2 cos x, because cos x times a half, 1/2 cos x. And that might actually be a little nicer for us to take the derivative of. So, now I just have a single chain rule. So e to the power of 1/2 cos x. Now it's time to take the derivative of 1/2 cos x. The 1/2 doesn't get affected. The derivative of cos is negative sign, so I'm going to put a negative in front of the 1/2. And there we are. All right. Next we have e to the power of sine x times cos x. So I have a chain rule because I have e to the power of a function, and I have a product rule up in my exponent. So the outside derivative is e to the power of, copy paste the exponent. Now it's time for the derivative of the inside function, which is a product rule here. So the derivative of sine x is cos x. Copy paste the second function, plus the derivative of cos x is negative sine x, so I'll actually turn that addition into subtraction. And now copy paste the first function, which is sine x. And I could always clean this up to cos squared x minus sine squared x, which I could also turn into the cos double angle formula. So I could write this, if I want it in its cleanest form, like that, as an option. All right, next one we have a quotient rule. So the derivative of the numerator is e to the x. I'm going to copy paste the denominator, minus the derivative of the denominator is 2x. Copy paste the numerator, all over x squared all squared, which is x to the 4. And x can't be 0 here. Okay. If I wanted to do anything with this, I might say, oh, there's a little bit of a GCF. So If I wanted to clean this up, I see that both terms have an x in common. They both have e to the x in common. And when I factor it out, I'm left with x subtract 2. And then I could even say, oh, I can cancel out an x there, so that I'm just left with e to the x times x minus 2 over x cubed. And that's something I would do if I had to do more with my derivative. All right, final one where we're just taking a derivative of more complicated functions. So for these ones, as you've probably noticed, you have to be very careful, make sure you're not losing track of anything. So here we have a chain rule because I see something to the power of 3. So that's the first thing I have to deal with, that outside function. Then inside, I have a quotient rule. And in my quotient rule, the numerator has a chain rule in there. So there's lots going on. But first thing I'm going to do, bring the 3 down, and then my bracket will be to the power of 2. The inside, just going to copy paste it. Not taking the derivative of it right now, because all I've done right now is taken the derivative of something to the power of 3, which is 3 something squared. There we go. Now it's time for my quotient rule. I'm going to take the derivative of the numerator, which has a chain rule in it. It's going to be e to the power of the original exponent, and now take the derivative of that exponent, so 4x minus 5. Now copy paste the denominator, subtract. The derivative of the denominator is cos x, and I'll copy paste the numerator. And that's going to all be all over sine x all squared, which I'm going to write as sine squared x. And there we have it. We're not going to clean this up. I'm not going to write the restriction here either, but I mean, actually, we can write the restriction here. We cannot have sine x equaling 0. So if you think about the sine x graph, 0, pi, 2 pi, 3 pi, and so on. So my restriction would be that x cannot equal pi times n, where n is an integer. Okay, so the purpose of the past few derivatives was just an exercise in being careful, taking your time and not losing track of what you've taken the derivative of and what you haven't, and just mixing and matching all the rules that we have pretty much. Now our final question is a word problem. The effectiveness of studying for an exam depends on how many hours a student studies. Some experiments show that if the effectiveness E is put on a scale of 0 to 10, then E at T equals that expression, where T is the number of hours spent studying for an examination. If a student has up to 30 hours of studying, how many hours are needed for maximum effectiveness? So this 30 hours gives us a restriction that T has to be between 0 and 30 hours. And we're trying to maximize this scenario, which means maybe the maximum effectiveness occurs at 0 hours or 30 hours. So we'll test those. Or it's occurring at the critical point, which is when the derivative is equal to 0. So step 1, just thinking back to our optimization, is finding the derivative of E at T. Now, that 0.5, if you want to distribute it in, you can, but that 0.5 isn't going to affect our derivative because it's just a constant. So I'm going to leave it out front. And now I'll take the derivative of the inside. The derivative of 10 is 0, so I'm not going to write that. And then for t, e to the power of negative t over 20, that's a product rule. So the derivative of t is 1, and then I'm going to copy paste the second function, plus The derivative of e to the negative t over 20 is a chain rule. So e to the power of e negative t over 20, and then I'll multiply that by the derivative of the exponent, which is negative 1 over 20, just the coefficient of t. And then that will get multiplied by the first function, which is t. Okay? Now at this point, I know I'm going to have to set my derivative equal to 0. And I want to do a little bit more factoring here because I notice both terms have this e to the power of negative t over 20 in common. So I'll add it to my common factor. And when I factor it out from the first term, I'm left with 1. When I factor it out of the second, I have negative 1 over 20t. And now I can branch out and set each side equal to 0. Now when I do e to the power of negative t over 20 equals 0, that has no solution. When I do the other one, I can isolate for t. So I'm going to bring the t term over and multiply both sides by 20 to get 20 hours. Now, this is where the derivative is equal to 0, but just like we did in the previous unit with optimization, we do have to test the endpoints and the critical point. So I'm going to test the effectiveness at 0 hours, at the 20 I just got, and at the maximum hours of studying. Okay, and if I punch 0 into my calculator for the equation for t, I end up with 5. So on a scale of 0 to 10, half effective. When I sub in 20 for t, I get approximately 8.68, so that's better. And when I plug in 30 hours, I get 8.35, so not as good. So this is the happy spot. So therefore, the student should study 20 hours. All right. Actually, we do have one more little word problem here about bacteria. A population of bacteria grows according to the function p at t equals 500 e to the power of 0.2t, where t is measured in hours. Find the rate at which the population is growing after 5 years. So we're just looking for the instantaneous rate of change when t equals 5, which means I need my derivative, and then I'll set t equal to 5. Now, when I'm taking my derivative, the 500 does not affect the derivative because it doesn't have a variable, so 500. And again, that's because of the product rule. If I did see it as 500 times e to the 0.2t, when I take the derivative of 500 the first time, it's 0, and then it'll be plus 500 times the derivative of the second function. I'm just not writing that first step because I know it cancels out. And now, the derivative of e to the power of 0.2t is itself times the derivative of that exponent, which is 0.2. And now I'm just going to plug in 5 for the time. And if I do that, I get approximately 272 bacteria. And time is in hours, so per hour. So at exactly 5 hours, this is the population growth. And that's it. This is our little intro to the derivative of a very specific exponential function. We will be looking at general exponential functions as well, but for now, we've been introduced to Euler's number and to the derivative of e to the x with all the other rules involved and a little bit of application.